Okay, this is going to be, I get questions about this all the time. The lunar reflector that the Apollo 11 left on the moon proves it went to the moon, and it proves that, the distance of the moon and all kinds of stuff. I want to dispel, we never landed people on the moon. We could have theoretically gone there mechanically, but I don't even think they did that. Now, if you look into a 1962 copy of National Geographic, look up the story Bouncing Lasers Off the Moon. They were doing that 7 years before the lunar lander, the supposed Apollo 11 landing, and you can bounce lasers off the moon. You're not hitting the reflector. What you're doing is you're hitting the moon and convincing yourself that it's you've hit the reflector. It doesn't matter where you hit it, because remember they landed in the Sea of Tranquility, which is a natural basin. It's a natural reflector. So if you just get it, you can bounce it off any of the mares, the craters on the moon, and it'll come back to the Earth. And I want to point out some problems. So that's only a 10 by 10 reflector, 10 feet by 10 feet, and you're firing a laser from Earth. So this is Earth, this is a representation, this is not the scale. Now, however, from this point to that white, see that white ball straight ahead of me? We're gonna walk to it, that's the moon. Now that's the scale from here to here. It's 108 of whatever the diameter that you're using as the moon, from the Earth to the moon, whatever you're using. I want you to do this experiment yourself. So, you're somewhere, I like to bring up the, because a lot of people saw it, if you ever watched Sheldon and all of them on the Big Bang Theory, they fire a laser, they go on the roof of their thing and they fire a laser, and they got the laser receptor right next to it. Well, remember, according to NASA, the Earth rotates 1,064 miles an hour at the equator. There's some point on the Earth, if that number is correct, where you're standing at the North Pole and it takes you all day to turn around. So let's just say you're halfway up there. You're going to have to figure out the spin of the Earth at that point. So let's just say it's half the speed, or let's say it's 600 miles an hour. So you're firing your laser at 600 miles an hour, and you're going to try to hit a 10 by 10 piece of aluminum reflector on the moon. So you fired your laser. Now, the speed of light is going to take you is 186,000 miles a second. So if the moon is 238,000 miles away, it's a second and some change going up there to the moon. And we're going. And then we hit the Sea of Tranquility. Let's just call this dark spot the Sea of Tranquility. Let's just call this spot the Sea of Tranquility. It bounces off a 10 by 10 reflector, and then we go back to the Earth. Again, light travels 186,000 miles a second. So you've got basically I'm gonna err on the side of caution and call it 2.3 seconds lag time. I'm giving everybody more than they deserve on this. So light goes at that speed at a vacuum, but remember, the first maybe quarter of an inch off of this, you've got atmosphere, so that's changing it up quite a bit. So if you're moving 500 miles an hour, let's say you're on the part of the Earth that's moving 500 miles an hour, in 2.3 seconds, how far does the Earth rotate underneath the moon? Figure it out. 2.3. That's where your acceptor needs to be from you. Now, all the acceptors, when they fire the laser, the acceptors are right next to it. They'd have to be, in some cases, depending on how close they were, how far they were south, they'd have to be, if you're traveling 1,000 miles an hour at the equator, and they've done the experiments at the equator too, and they've gotten the same thing. So 1,000 miles an hour divided by 60, you have to have your acceptor, let's say UC Berkeley, you've got to have it 600 feet away, 700 feet away, yet they have the acceptor right next to it. So they're convincing themselves that they're hitting a 10 by 10 reflector when all they're doing is hitting the moon, and it's bouncing off the natural depression of the mares, the Sea of Tranquility. It's also called a mare, which means sea in Latin. But so these people that think they're hitting the 10 by 10 reflector, they're just hitting the Sea of Tranquility, where they claim the reflector is. But do you really think you can hit a laser as the Earth's moving and the moon's moving and there's atmosphere, so you have to take into that to hit a 10 by 10 reflector? You're high if you think that's happening. And like I said, look up the National Geographic story in the early 60s of where they bounced lasers off the moon. It's there, and it's not that hard to look up. So what they're doing is, anybody that's firing a laser off the moon, they're hitting the Sea of Tranquility, which is a natural reflector. Remember, it's like a shallow indentation, and it's bouncing it straight back to the Earth. It's been done before, and 7 years before the supposed lunar landing. But no human beings have ever been through the Van Allen radiation belt. The only missions that had human beings that they claim went through the Van Allen radiation belt were the Apollo missions, not Apollo-Soyuz. Apollo-Soyuz is well within the Van Allen radiation belt, and my moon fell over here, so I got to pick it up anyway. So there you go. And it's also another funny thing. The only people that were allowed on the lunar missions were Masons, Freemasons, who know how to keep a secret. So I used to be mad at all the astronauts for screwing around and doing this, but they were just doing their duty. Remember, they were almost all of them were Navy pilots, and we had to beat the Russians to the moon. It's all a big scam. We always talk about going back to the moon, but we never actually do it because we can't. We can't even, we have to rely on the Russians to get people up to the International Space Station, which I have problems with also, but that's for another video. Anyway, like, share, and subscribe if you would. Thank you. I am out.